So today we're going to talk mainly about classical field theory, and there are certain results that are very nice and important. And in fact, because these results are so nice, as I said to you before, people in the 19th century, many physicists thought that the chemists were nuts to talk about the dirty little atoms and molecules, and that they just talk about fields and so forth. Anyway, let's see, I have to pay the TA. Are there any questions? All right. So, last time, let me just review something that I think you all know, and it's that you have a Lagrangian. And by the way, the Lagrangian in classical field theory is something so that when you integrate over all of space and time, you get something called the action. And this is supposed to be invariant. And so that means that L, the action density, has to have all the symmetries of the theory. Now, once we're given L, we then say that the momentum conjugate to the field phi is the partial of the action density with respect to the time derivative of phi. And then we say that the Hamiltonian, or the energy density, is pi phi dot minus Lagrangian, or the action density, and I'm taking this in the simple case where L just has well, this is quite general, but I was thinking of one field, is what I'm trying to say. If there are more than one field, then you have several fields and several conjugate momenta, and then what you would have, H would be a sum over the different fields, pi sub n, pi dot sub n minus L. Now, we normally restrict ourselves to Lagrange or to action densities that involve the field or fields and the first derivatives of the fields, and normally not higher derivatives of the fields. Now, that is just what we do normally and what we'll do in the standard model and so forth. The simplest case is where the action density is simply a half. You can write it as, let me use Roman when I think of it. That's the kinetic part. That's a mass, and that's phi squared. In this case, the action pi is partial L, partial phi dot, or the time derivative with respect. So that's the time derivative, that gives us this, but the thing is squared, and so we just wind up getting phi dot. And then H, the energy density, is pi phi dot minus L. Well, that's just phi dot squared minus L. But this L, by the way, let me demystify it as a half phi dot squared minus a half grad phi squared minus a half m squared phi squared. And so when we subtract here, we're subtracting a half phi dot squared plus a half grad phi squared plus a half m squared phi squared. And so altogether this is just a half. Well, what we do if we want to be correct, we switch from phi dot to pi, and so instead of using phi dot, we use pi here. So this is a half pi squared plus a half grad phi squared plus a half m squared phi squared. Okay. So you can think of this part as the kinetic part, and this part as the potential. Or in this case, if you want, you can consider the whole thing as kinetic. Or you can consider the pi squared as kinetic and all of this as the potential. It's to some extent a matter of taste. Okay. Now, Schwartz mentions various notation. You should look at it. Pi and phi are for scalar fields. One uses somewhat other Greek letters, psi, psi, chi for fermions. For vectors, you typically use uppercase Roman letters. And for tensors, well, you have two subscripts, and you know, what else could it be but a tensor? All right. So let me now get to the first of two important things. You've probably seen this before. I hope that my presentation is the clearest of the ones that you've seen. I'm going to try to make it really clear. So we have this action, which is an integral of the action density over space-time. All right, now this is, what we're about to do is the principle of stationary action. What does that mean? That means that the first order change in the action is zero. So this is the first order change due to arbitrary tiny delta phi's. And what we're going to say is these delta phi's are arbitrary, but they vanish outside of some space-time volume. Okay, so we're going to say that delta phi is non-zero only after the Civil War and only up until 2100, and only works in this galaxy. Only is non-zero in this galaxy. And then what we'll get is equations of motion that hold now and here on Earth, which is good enough for the moment. The point is that this guy here is just a mathematical thing at our disposal, and so we can have it zero at large space and time values. All right, so what's the change in the action? Well, the change in the action is, of course, an integral of the partial of the action density with respect to the fields, change in the field, and just to keep things uncluttered, I'm going to assume there's just one field. If there were more than one field, we'd sum over the fields, of course. And then you take the derivative with respect to, let us say, the eighth derivative of this field, and we need to put in the change in the eighth derivative of the field. So just to make sure we know what we're doing here, dA phi just means partial phi, partial x a. Okay? All right. Now, what is the change in this derivative? Well, the change in dA phi is dA of phi prime minus dA of phi, obviously, where phi prime is phi plus d phi. And so this is dA of phi prime minus phi, and that's dA of the change in phi. So the point here that I'm emphasizing, just because it's skipped in almost every book. It's that the change in the derivative of the field is the derivative of the change in the field. And okay, so that means, and we don't have to go any higher because we're only considering action densities that involve the field and the first derivatives. All right, so the change in the action then is an integral of partial L, partial phi, change in phi, plus this term, which is partial L, partial dA phi, dA partial phi, and all that before things. And now we do our usual integration by parts, and we have this partial L, partial phi, change in phi. We first write this as a huge derivative, dA of partial L, partial dA phi, d phi. But now this one has a derivative acting on this, which we want, but also on this, which we don't want. So we have to subtract dA of partial L, partial dA phi. And then that's all multiplied by delta phi, and all that's inside the full x. Okay? Any questions? Or any corrections? Or just ask a meaningless question and I'll throw you a candy. All right. Now we then put these two together because they both have a simple factor of delta phi. So this is an integral partial L partial phi minus dA of partial L partial dA phi, all that's delta phi, and then we have a derivative here, total derivative as we say, of partial L partial dA phi delta phi d4 x. Okay, well we can obviously integrate this and we get a surface term, but when we do that surface integral, it goes out to space and time at infinity, and we chose to have delta phi vanish there, so this thing goes away. And so altogether, this is equal to an integral of simply partial L partial phi minus dA partial L partial dA phi delta phi d4x. So this is the first order change. We want this to vanish for arbitrary delta phi in the here and now. And so that means in the here and now, partial L partial phi minus dA partial L partial dA phi is 0. And so this is then the consequence, this is the equation of motion. And this is very, very general. I mean, I'm doing it here for scalar field, but in general relativity, it's the same thing, basically.
So what I never understood about this, maybe someone explained to me, but it never stuck, is why can't you just, so you can have the integrand go to 0, but why can't you just say, well, maybe if we have the right boundaries, the integral itself will go to 0 when we evaluate the integral?
Have the right what?
So you're saying the integrand is 0, right, by saying, writing that out?
I'm saying that we can throw away this term.
Right.
Because we define delta phi to vanish at big values. And then the principle of stationary action says that delta S might have terms like delta phi squared, and I didn't even include them here because you'd have the second derivative of L with respect to phi squared times a half delta phi squared, and then higher terms and so forth. I'm ignoring them because I'm allowing that the change in the action should be quadratic in delta phi. But what we've computed here is the change in the action is the integral of this,
Right.
and this has to vanish for arbitrary delta phi, so we can have a delta phi that vanishes everywhere except in the neighborhood of some small space-time point, and there it's big.
Okay.
That's the idea. Any other questions? Okay, so this is the principle of stationary action. Now, one of the nice things about path integrals is that this follows from the path integral formulation of quantum field theory, or equivalently of quantum mechanics. And the basic idea is that the amplitude for this to turn into that is a sum of exponentials of I times the action for every way that this could go into that. And so if there's a path, a process that takes you from this to this that has stationary action, then there are all sorts of processes from here to there that have almost the same phase, and so they reinforce. If, on the other hand, from here to there's no process connecting them of stationary action, then when you add up all those e to the I actions, the phases cancel and the thing just washes out. And of course, in the quantum mechanical path integral, you have to have the exponential dimensionless, so you divide by h bar, it turns out. And so that means there's very little wiggle room left when you divide by h bar. There's the slightest wiggle and you get, it's all gone. And the other thing is, of course, that if you have a process whose action, if you're considering if from here to there can be done with a process that has an action smaller than h bar, well, then anything goes. Okay, you can have anything happen because you're never going to wash anything out. Everything's going to count. Any questions? Okay. Well, let me give an example of this. The example of this, of course, would be this particular action density. And if I take the derivative with respect to that, partial L, partial dA phi, well, this is just, well, it comes in twice, so it's just d upper A of phi. And the partial with respect to phi, of course, is minus m squared phi. So the equation of motion then is dA of this, which is d lower A, d upper A of phi, is equal to m squared phi. And this is something that we call, let's see, minus sign here. Left arm was down, you need to watch that. And so the equation is box plus m squared phi is 0. So that's the equation of motion for that. Okay, the next topic, this is actually kind of interesting. When I was, I don't know if I was a graduate student or whether it was later. At some point I was at Harvard. And somebody, I don't know who it was, some famous theoretical physicist, was showing us what's known as Noether's theorem, which I'm about to go to show you. And it turned out that none of us had heard of it. And
Sidney Coleman was away, giving a lecture in New York or something, I don't know. And so I listened to it, and when Coleman comes back, I was able to explain it to him. But, of course, this is my memory 50 years ago, so it could be that I've misremembered. In any event, let's learn about Noether's theorem. Noether, by the way, is Emmy Noether. She was born in Bavaria, Germany, and came to the States and then taught at Bryn Mawr. She was basically a mathematician. So here's the idea. Suppose we have some way of changing the fields so that we have, in a way that depends upon some continuous parameter, and for some reason I'm lapsing into Greek because all these symbols are Greek. So this is how phi can depend upon alpha, and there are various ways in which this might be, in which phi might change. And suppose that when you have that L of phi of x and alpha and the derivatives of phi of x and alpha, suppose that's just the same as L phi dA phi. Okay? And we're thinking here in terms of a global symmetry. We could have a gauge symmetry, but global is good enough. Global means that alpha is a continuous parameter, but we're not going to use different alphas at different points in space-time. Okay, so what do we have here then? We have a simple equation. Partial L, partial alpha is 0. All right. So let me get the consequences of that. 0 then is partial L, partial alpha. And I think I will put in a sum over different fields. So now we're supposing there are several fields, and as you change alpha, they all change one way or another. Let's see, I think maybe we'll get better ventilation if we open this. Whatever was causing the noise is gone. Okay, so what is this? This is partial L, partial phi n, partial alpha, plus partial L, partial, let us say, all right, I'll say dA phi. Change in dA phi, and this would be partial alpha of, well, let me see, this is partial alpha of dA phi. Okay, so that's the change. Now, we can write this in different ways. We can say that this thing, of course, we can take the dA out and put it in front of the d alpha. So we can say that this is a sum on n, partial L, partial phi n, oh, there's an n here. Partial phi n, partial alpha, plus partial L, partial dA phi n, dA partial phi n, partial alpha. Okay. So, the next thing is, let me just, we're just going to do a sort of backwards integration by parts. I'm going to write this as dA of partial L, partial dA phi n times this thing, partial phi n, partial alpha. But now this derivative here, when it acts on both of them, so when it acts on the second one, we get this term, but when it acts on this one, we get a mistake, unless we subtract it. So then we have, what we have here then is a sum, partial L, partial phi n, minus partial A, partial L, partial dA phi n, and all of this times partial phi n, partial alpha. Okay, so in other words, this term just cancels the derivative when it acts on the first term. Okay? Okay, now, here's the key point. Noether's theorem is about fields that obey the classical equations of motion, or equivalently fields that obey the principle of stationary action. So consequently, this thing vanishes. So what we get then is 0 is sum on n of the derivative with respect to xa of partial L, partial dA phi n, partial phi n, partial alpha. And now, you might be a little bit worried by this because it's got this screwy parameter here that just is from some symmetry we've noticed. But what the heck, this is just something that has an upper index A, and apart from that, it's something or other. You know, who cares? So this is a sum on n dA of, well, effectively it's JA. I shouldn't have put that sum there. So we have then this rule, 0 is dA JA, and JA is the sum on n, partial of the action density with respect to the 8th derivative of the nth field, and then times the derivative of the nth field with respect to the parameter of which the action density is independent. All right, any questions? This is Noether's theorem. This is the equation for a conserved current. And I'll explain that in a moment, huh?
Just like an arbitrary current?
Well, a conserved current, but the thing is pretty arbitrary because this is a very general possibility here. Here. Whoa!
Okay.
All right, so, any questions? This is important. And it's also quite simple, you see, it's just talk, but it's very counterintuitive. In fact, it's so counterintuitive that I had to pause here, because I changed the notation from my notes, so I was sort of ad-libbing to some extent. But see how straightforward it is. It's just the Lagrangian doesn't depend upon the action density doesn't depend upon the parameter. Then we screw around with partial integration, with not partial integration, just the essence of the integration by parts is just taking a simple derivative and making it complicated. And then we say, well, the classical equations of motion, the fields obey the classical equation of motion, and what we're left is 0 equals this. This then is the current. Now, let me explain why these currents, why this is a conserved current. Q, which is the integral of J0 d cubed x, this is more or less time independent. And let me say in what sense it's time independent. But it represents a truly conserved charge. So the integral of q over some volume, what is its time derivative? Well, q dot is d0 j0 over v, d cubed x. But d0 j0, oh, let me just make sure we understand what this means. We're summing over these things. The up index is the natural index for the current. The lower index is the natural index for the derivatives. So this is just time derivative of J0 plus the divergence of the current J. Okay? All right. So that means that this is minus the volume integral of the divergence of J. And then by, somebody wrote this theorem, this is minus the integral of J dot d what? D area, say. Over the surface, over the boundary of V. Mathematicians like to write it as partial V. They have complicated pleasures. All right, so the change in the charge in a certain volume is equal to minus the amount of stuff flowing out, current flowing out. Well, of course, that's what you expect for a conserved charge. You don't expect that the amount of electric charge in a certain volume is always going to be conserved. Instead, whatever the time derivative of the charge is inside a volume, it's equal to minus the current going out. And so if you have a lot of current going out, you have a lot of leakage, the charge is going down. All right. These things are called Noether currents, and they play a big role in the standard model. And what I'll do is I'll give you a simple example, and then maybe I'll say something about a more complicated example. Any questions, though?
So you managed.
Do you want candy, or are you still abstaining?
I'm still abstaining. So you picked a sort of an electrodynamically motivated example where the idea of current makes sense. But what about things like rotations or rotational symmetry? How do you kind of map this idea of a current or a flow? Aside from like the obvious, like change of an angle.
That's a very, very nice question, and of course, the consequence of rotational invariance is conservation of angular momentum.
Right.
And normally when you think of Noether's theorem, we normally think in terms of rotating fields into each other, as in the standard model. And in the standard model, we let the rotations vary from place to place. I tell you what, I'll try to, on Monday, I'll try to work in something related to what your question, but that was a golden question. It's just that I did not in my notes prepare a golden answer. I'm just giving you the silver answer, which is for the just ordinary electric charge. And so, over here, on those on those green boards, and over here we've been talking about a single scalar field or several scalar fields. Now we're going to talk about two scalar fields, and maybe I'll just add a little bit here that Schwartz skips. What we actually have here are two fields, phi 1 and phi 2 of this, that describe particles of the same mass. And then we say, phi is going to be 1 plus I times the other divided by square root of 2. Okay? And so then we say phi star phi well, that's 1/2 phi 1 squared plus 1/2 phi 2 squared and so forth. So, and phi star, of course, is phi 1 minus I phi 2 over root 2. And it makes sense to do this if the particles have the same mass, then you can put them together. And the standard model one does this before the Higgs field gets to its mean value in the vacuum, but where the Higgs field, one imagines the Higgs field is still 0, and in that case all the particles are massless, and so you can lump them together, you can make these complex fields and complex multiples and so forth. And, all right, so in terms of that complex field, I want to have an action density that is d mu phi star, d mu phi, or let me use Roman, dA phi star minus m squared phi star phi. Okay, so that's the picture. We have a single scalar complex, a single complex scalar field. Okay, well, there's an obvious symmetry here. You can multiply phi by a phase, and then phi star gets the opposite phase, and L is invariant. So phi of x and alpha is just e to the I alpha times phi of x, and you could even put an e up here if you want. Charge. Right. Might be nice to do that, so I'm going to throw in an e. It's not the same e. This is 2.718281828 dot dot dot. And in this e, well, this I should call this q. Okay, so once again, 0 is partial L, partial alpha. J mu is, well, let's use JA. JA is partial of the action density with respect to dA phi times partial phi, partial alpha, plus partial L, partial dA phi star, partial phi star, partial alpha. And so JA is equal to, well, the first term is partial with respect to dA phi. Well, that's just d upper A phi star. And by the way, d upper A is the same as d lower A except for the space indices, and then there's a minus sign. What is the derivative of the field? Well, it's just IQ phi. And so this is IQ phi. And then the next one is the derivative with respect to phi star. Well, that's dA phi and minus IQ phi star. And so our current here is I'll write it as minus IQ D, sorry, I was on the wrong line. Minus IQ phi star dA phi minus phi dA phi star. All right, so that's our current. And this current then should satisfy the, should be conserved, that is to say dA, JA should vanish when the equations of motion are, when the fields obey the equations of motion. So this is minus IQ, and now we have the dA coming through, and we have dA phi star, dA phi, plus phi star, d lower A, d upper A, that's what we call box phi, minus
d lower a phi, d upper a phi star minus phi box phi star. Well, these two guys cancel identically. And then we have these two, which certainly look as though they've gone to school together. So now we apply the equations of motion. The equation of motion on box phi is minus m squared phi. So this is equal to minus iq. Whoops, there's a minus sign. Minus m squared phi star phi plus m squared phi star, and so that's 0. Okay, so the current is in fact conserved. So that's the check. JMU is a conserved current. So global continuous symmetries of the action density imply the existence of conserved Noether currents and conserved structures. All right, now there's a related, I said there were two really important simple things that are very nice. I was wrong, there were three. The third is another kind of conservation law that's a little closer to what you were talking about, but it's that the action density is independent of the date and the location, the GPS location, say. In particular, when you get the action, you take it out of the box, the box doesn't have a use by date. Okay? So that means that the action density has a vanishing derivative with respect to time and space. And that vanishing of that time derivative, together with the classical equations of motion, give us the conservation of energy and momentum, and for that matter, angular momentum, but as I said, I didn't write that down up. Any questions? Trying to think of the joke. I actually had several ready yesterday. I forgot every one. Well, the reason I'm so bandaged up is that I saw my dermatologist today and gave me 3 shots of liquid nitrogen in the face and 3 biopsies, which he tells me are probably not serious skin cancer. Anyway.
Why are they injecting liquid nitrogen?
What?
Why are they injecting liquid nitrogen?
They don't inject, he sprays it.
Nice.
He carries around a quart or so of liquid nitrogen, an insulated thermos, and has a sort of spray thing. So the liquid nitrogen freezes whatever the growth is, and then eventually the thing forms a scar, and that'll look worse than usual, and then the thing eventually heals. Sorry. All right, maybe I'll think of a joke later. Okay, let's do the energy momentum. We have 0 is By the way, am I making things more confusing by using Roman subscripts? I mean, I can do Greek if you want. I went to a high school where they tried to keep us unaware of all of the progress since Galileo by having us study Latin and Greek. And so I do know my Greek letters.
All right, so that vanishes. What is that? Well, it's partial L, partial P. Let's go to the case of a single field. If you have several fields, of course, you sum over them. And now here I'm going to have to say, okay. And now I'm going to write this thing in a tricky way. I'm going to say this is delta delta A partial, oh, I did use A, I'm going to use B then. Delta B dBL there. So this, of course, is the same as that. We're just using notation. Sorry. Now, we have our field equation. What are the field equations? The field equation, of course, say that this thing, partial L partial Phi, is equal to dB of partial L partial dB phi. So we've got two equations then on the board. The first one says that the action density doesn't have a use-by date, and the second equation says that the fields obey the classical equations of motion. Okay, that means that in this equation we can substitute for something simple, something complicated, but it's actually a good idea. And I'm also going to bring this in from the other side. This reminds me of something Glauber once said to me, and I didn't quite appreciate it at the time, but he said that progress is often made by taking one step backwards. And we've seen several examples of that in these derivations, where you start with something simple, and instead of trying to make it simpler, you make it a little bit more complicated, and then you simplify things. And so progress is often made that way. Okay, so let's combine that. And we're going to take this top equation, we're going to write it using this. And so what we get here is dB partial L partial dB of phi. And then we multiply by dA phi, that's this term. And then we have this term, which is partial of L partial dB phi times dA dB of phi. And then we're subtracting the thing from over there. And so all of this is 0. Okay, now you notice that it's actually a total derivative. In other words, we have a dB here. And here we have a dB that's hitting first the factor on the left, and then the factor on the right, if we interchange these two. So let me do that. Let me make that BA. All right. So what this says is that 0 is equal to dB of partial L partial dB phi partial A of phi minus delta BA of the action density itself. All right. So we've got a bunch of conserved currents that hold. This is sort of Emmy Noetherish, but it's a little different. When the equations of motion obey, and because there's no use by date or use only in the US or something, not for export. And so this is our equation, and we have then a conserved current. And here it's JB, and JB is partial L, partial dB of phi, dA of phi minus WBA of the action density. And so you notice that this is something that has two indices. And so in fact one normally writes it as TBA. So this is the energy momentum tensor. And it is for conserved tensors. And because it was derived in this simple way, it's called a canonical energy momentum tensor. There's a nicer energy momentum tensor that's actually symmetric, and let me write TBA, so I'll raise the second index, and this would be partial L, partial, I haven't done anything to B, so this is still dB of phi, but now I've raised the A, so it's dA phi minus, and raising the A means we have A to AB, so A to BA, action density, okay. This thing, obviously the second part is symmetric because you interchange B and A. Eta is what Schwartz uses, G4 or G0. It's just 1 minus 1 minus 1 minus 1. But this part isn't guaranteed to be symmetric. But you can write, for any given theory, you can construct a slightly different energy momentum tensor that's also represents four conserved currents. And these conserved currents guarantee the conservation of energy and momentum. And this is true in all classical field theories, including general relativity, no matter what a certain colleague of mine says. Okay. So this is the, as I said, the energy momentum tensor. Let's look at some of it. First of all, energy. Well, the energy part is, the energy density is T00. Oh, and let me here put the equal sign there and put a sum over n, because I didn't want to, make it more complicated. But you sum over all the fields, obviously. You don't leave anybody out. And of course, that's because if you take the derivative with respect to x, you have to conclude the change in the action density due to the change in the position of every field, not just one that you particularly like. But the sum is only over this part. This part doesn't get summed. Okay, so what's conserved? What's conserved is the energy, and this is an integral of T00 d cubed x. And the momentum also is conserved, and the ith component of the momentum is an integral of T0I d cubed x. And what is this in this particular case? Well, let's go to the simple scalar field theory that's on the green boards up in the front. The scalar field, single scalar field of mass m. Then what is this? Well, this is integral partial L partial phi dot, or if there are several fields, phi n dot, and then di phi n d cubed x. And so for that simple theory, this thing is minus phi dot grad phi d cubed x. And in that case, what we would have, that would be p vector, the conserved momentum. And for the for the energy, it would be an integral of phi dot squared minus L d cubed x, and this is integral phi dot squared a half plus a half grad phi squared plus a half m squared phi squared. So that would be the energy density. And you recognize this as the Hamiltonian, where we've reverted to phi dot for the momentum. Okay, any questions? Now, remember here that, as I did over there, it's the sense in which the energy or the momentum is conserved is that the amount of energy inside a certain surface need not be conserved, but its time derivative is minus the flow of energy out. And similarly, the amount of momentum inside a certain surface has a time derivative equal to minus the amount of momentum flowing out. So it's that sense. And in particular, if you are dealing with energy and momentum conservation, or angular momentum conservation in general relativity, well, you're talking sometimes about the whole universe. And so you have to worry about what the fields are at infinity. You can't just say, oh, we don't have any funding to support those fields out there, so there's zero. Instead, what you say is that you keep the surface term and you see whether it's there or not. And if it's there, if it's non-zero, then you keep it. If it vanishes, well, then you've got the energy conserved in some finite quantity. And in particular, when you talk about the universe, expanding from some small thing and all this dark energy, what's actually happening is the energy is conserved, but there's some negative gravitational potential energy compensation. And then, of course, surface transition. All right, as I said, this field, this thing is not always symmetric, but and so you might say, well, all right, what's the recipe for a symmetric energy momentum tensor? Well, there's some guy by the name, some physicist by the name of Belafonte or Ballantyne or something. I mix them up with Harry Belafonte, the singer. And so I don't remember what this guy's name is. I'm not very good at names anyway. And if it has more than 2 syllables, forget it. So anyway, he had a recipe, but there's a simpler recipe, and it has to do with general relativity. What you do is you consider the matter action, and then you consider what happens to the matter action if you make a small change of the space-time metric. Okay. And so what you do is you then write the change in the matter action. So you have to know what the matter action is. So what's the matter? And then you write down, you express this as a half d4 x square root of minus the determinant of g mu nu. Or plus the determinant. Well, it's almost always negative. T mu nu, I've become Greek all of a sudden. T mu nu of x. Change in g mu nu of x. So, and of course, this is the first order change in the matter action. You just write it this way. This is automatically symmetric because that's symmetric. All right, and you can think of this as AB if you want to get confused. Okay, this automatically gives you a symmetric tensor, and this symmetric tensor turns out is always conserved. Okay, although the conservation law is a little more complicated in GR, you would say something like the covariant derivative, so d mu nu semicolon mu. For the vacuum, I can just mention what it is. It's T mu nu is F rho mu, F rho nu minus a quarter G mu nu, F rho sigma, F rho sigma. Okay. This happens to be the energy density for electromagnetic fields in vacuum, or for the electromagnetic, classical electromagnetic field. You notice it's clearly symmetric. If you do the canonical one, what you get is something like this, but you only get half of one of the F's. You get a sort of D rho of A nu instead of the whole thing. All right, now, Schwartz mentions that there are various kinds of currents, and what he's doing is he's explaining the jargon of the trade. So there are, first of all, the Noether currents that I just described. Then there are external currents. Let me show you an external current. This is an external current, okay? Then there are currents where we're just writing L of x is dot 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 minus A mu J mu. Okay, this is the external current. And it could be that we just want to, when we write this down, we're not interested in how J came into existence. We just want to see how A responds, how the electromagnetic field responds to the current. And then finally, it can be just as, we sometimes write it this way, as a placeholder for something that we're going to analyze later. So later we say something like J mu is I e phi star d mu phi minus phi d mu phi star with a plus or minus sign, or it's equal to E psi bar gamma mu psi. Those are examples. So the various, we'll understand this later, but anyway, so those are the various currents. All right, any questions? Yes.
So for this T tensor, what do the T1I?
Give me that again now?
So for instance, when we discuss the momentum,
Yeah.
we look at T0I.
Yes.
Right, so what are the T1I,
Ah,
T3I?
those are the currents of momentum.
Currents of momentum. Well, you said a word, but that really doesn't say.
Well, I mean, let's look at what this equation is. It's something like this. And since I'm doing this on the fly, I may not be getting the indices entirely right. But what we have for conservation of energy is, let us say, dA, well, this is the whole thing. This is energy momentum. Okay? So if we're talking about energy, then this would be like this. It would be 0 is dA, TA 0. Okay. So Ti0 would be a current of energy. It would be the energy flowing out through the surface.
Oh, you mean an exact analogy to
Yes.
Oh, okay, okay, gotcha.
And then in the other case where it's momentum, it would be 0 equals dA TAI. And now, so T0I is the momentum density, but TJI is the current flowing in the direction J. Oh, the current of momentum I flowing in direction J.
Right,
All right.
okay.
All right. Good question. You sure you don't want a candy?
All right.
Yes?
No, thank you.
Okay. So we we have a few minutes to do classical electrodynamics. Quantum electrodynamics is often written QED, so this is CED. And so let me go through this for you. You know, I think actually I misremembered the Noether theorem. I think I was just in the room when somebody was explaining it to Coleman. The idea that anybody would explain anything to Coleman was just such a shock. That was it was Stephen Adler, actually, who was explaining the terms to Coleman. All right, so let's look at classical electrodynamics. Here the action density is -1/4. This blackboard isn't very, well, this green board isn't very good. FAB minus AB JB, okay. So, obviously, we need partial Lagrangian with respect to AB. Well, that's pretty simple. That's minus JB. So we got that part of Lagrange's equations pretty easily. Now this FAB, I'm going to take it as FAB is DAAB minus DBAA. You notice I say I'm taking it as because in half the books it's this way, and half the books B and A are interchanged. And of course they're always mu and nu, but the point is, but since the thing only occurs squared, you know, who cares? All right, so let's do the partial of the action density with respect to the C space-time derivative of the field AD. All right, so that's -1/4 partial FAB partial DC AD. All right. Well, obviously, I mean, you can rewrite this as you can raise these two and lower those two, so it doesn't matter whether you differentiate this one or that one, you just have to include a factor of 2. So I'm going to rewrite that as -1/2 FAB. Schwartz has a different way of doing it, and I like my way better. I'm sure he's doing it correctly. All right, so we differentiate that way. Okay, well, when A is C and B is D, this thing comes out as just a 1. On the other hand, when A is D and B is C, you differentiate this guy and it comes out with a -1. And so what happens is they actually add, or when that's true, this thing is, instead of being CD, it's DC. That's the way what I should have said. So the answer is -1/2 FCD plus 1/2 FDC. In other words, when B is C and A is D, you get a -1, which cancels this -1, but on the other hand, it's FDC rather than C. But F is manifestly antisymmetric, and so this is equal to -FCD. So altogether then our equations of motion are, is that is partial L, partial
partial CAD, which we've identified as minus FCD. So the, whoops, this, yeah, no, this is not equals. This is just that. And so the equation then is DC of FCD is equal to JD. Okay, I skipped the step. Does anybody want me to see me put in the step? No. Okay. All right. Now if we substitute for what FCD is, this is DC AD minus BD AC, which is box AD minus DD of DC AC equals JD. All right, in the Lorentz gauge, this vanishes. We're doing electrodynamics, so we have gauge invariance, and we can choose a gauge. Especially classically, you can choose a gauge just to work, to simplify the equations. And so if we assume 0 is DC AC, then our equations are box AD is equal to JD. Okay. On the other hand, this is also a very nice equation. These are the inhomogeneous Maxwell equations. The homogeneous ones I unfortunately didn't write down, but I think we can write them down as something like this: epsilon A, B, C, D, dB, F, C, D is 0, where epsilon is a four-dimensional, totally antisymmetric quantity. And this, I think, is told beyond PI. So those are the homogeneous equations. Del dot B equals 0. And curl of something plus time derivative of something else is 0. And I forget which one it is. Does anybody remember?
No.
We all should remember, but no, it must. Videotape, full part of the universe. That's terrific. All right. Anyway, continuing. In this, well, we've got 3 minutes left. Okay, Schwartz next wants to bring in effectively perturbation theory, and or simply to make use of the field equations and the nature of Fourier transforms. And you see, that's what Fourier really did for us. If you have an equation in which you have linear differential operators, then the Fourier transform is a huge advantage. And in this case, well, we have box, differential operator, linear in A equals something, and so there is a solution. And if we call the propagator for the electromagnetic field just 1 over box, then we can just write this as AD equals the propagator on JD. And of course, so you say, well, what the heck is 1 over box? And so we'll see what 1 over box is. It's not hard, it's just one of the Green's functions. Let's look at, and this is called the propagator. The hardest thing about propagator is spelling it. I'm guessing that that's right. I live with Wiki and Google. All right, let's consider the simple case where the J mu is simply a charge that's lonely and so depressed that it's not even moving. It's just sitting at a particular place. So J 0 is E delta cube of x, and j vector is 0. And so we can figure it, so we figure then that a vector is 0, and then little a is, a lower 0 is e over box times delta cubed of x. And this has to be interpreted, and we'll see what it means in a moment. Well, first of all, what is this delta function? We've just about run out of time. So let me just write down this formula. In fact, let me write this delta n. Delta n of x is integral dnk 2 pi to the n e to the I sum ki xi. So I'm 1 to n period. That's it. This is the delta function in n dimensions, and I'm just summing over the ki's. And of course, if you want to be fancy and throw in some screwy metric, it makes no difference at all, because you're just integrating over all k anyway. So you could put an arbitrary metric in there. All right, I think we can stop here because we've basically run out of time and jokes. Sorry, the velocity of jokes. Any questions? Can I get your pen?